I'm not going to play the movie. I'm only going to talk about the movie. Has anyone heard? Has anyone heard that factoring is supposed to be hard? Right? Now, frequently, even Bill Gates, I think, messed this up one time when he talked about factoring prime numbers. So what people mean is factoring numbers into primes, into their prime divisors. Okay, but yes. So it's the basis of some crypto. Okay, it's also it's believed to be hard unless you have a quantum computer. So one of the things that got people interested in quantum computing was Shor's algorithm, where Shor showed that you actually can factor quickly on a quantum computer. We don't know quite if we can build those and actually run Shor's algorithm on them yet. So factoring, yes, is the basis of a lot of cryptography, public key crypto systems, RSA, stuff like this, which you may have studied, or you will study, or you might have heard of, or something. Okay, so it's believed to be hard. It's hard enough that people will like protect your bank account using crypto based on this problem, on the assumption that people can't, given a large number, people can't find it. So you take two large primes, multiplying them is easy, but then given their product, finding those primes from the product is believed to be difficult. At least we don't have a polynomial time algorithm for it. But let's suppose that I give you, I have to start this again. Yes, okay. Let's suppose, I only have like 15 minutes. Faster, we must go faster, because I haven't got to Karatsuba's algorithm yet. Okay. So let's suppose that I say, what are the factors of n? Okay, so what you can do is just write for I equals 1 to n, if n mod I equals 0, print I, and if n4. How many steps does this take? Like n, right? So this is going to print, it's not just going to print the prime factor, it's going to print all the factors. So factoring takes linear time. That doesn't sound super secure or hard. But it takes time linear in n. Okay? So linear in n is definitely polynomial in n. But it's linear in n is exponential in the number of bits you need to represent n. Okay, so that's why it's hard, because when we're talking about problems, we're talking about how big a piece of paper we need to write the problem down. Okay, so just think of factoring. If you want to find out more about factoring, there's this cool movie, Sneakers, from like the early 90s, actually. It's got lots of great people in it. And actually I found out just preparing the lecture notes that Len Edelman, who's the A in RSA, which is the public key crypto system, actually he knew the director, and he wrote the slides for when the mathematician in the movie presents how to factor. So, yay. So presumably those slides are correct. Okay, so what's next? Factoring, knapsack, RAM model. Oh yeah, we have to talk a little bit about we're running out of time. Let's talk about the model of computation. So if you do more algorithms courses, I believe there actually is only really one more. Like there's Norbert's, and maybe there's computational geometry or something which could use this. Frequently we talk about something called the RAM model. Okay, we'll also talk about this Turing machine. Nobody really analyzes algorithms these days in terms of Turing machines, unless you're talking about like polynomial time or something like that. Because if you care about logarithmic factors, then you work on the RAM model, which is a more faithful representation of actual computers these days. So what is the RAM model? Well, so for us, if I talk about addition or something, usually I'm talking about numbers that fit in a machine word, and adding two machine words, you know, you have this what's called bit level parallelism, which means you don't have to do this like digit bit by bit. You actually have a table in your computer and it just adds, right? So you can do addition of two numbers that fit in machine words in constant time. Multiplying is a bit tricky because multiplying is not in a complexity class called AC0. But actually, yeah, you can sort of assume that you can multiply. As long as the stuff fits in a machine word, you're good. Generally, as long as as long as the operation isn't too weird. For example, you can't say, oh, well, this number fits in machine word, I can factor it in constant time. No, not that. But addition, multiplication, like I said, it's not AC0. So you don't really need to know, but But then these machine words, so on a modern computer machine, your machine words are probably 64 bits. Like, unless you have a really old machine. So these days, like everything, you can still get versions of software written for 32-bit machines, but I don't know if anybody still uses those. You generally have 32 bits or 64 bits. So the key thing is people talk about, we've got a word RAM, and then let's say theta. So theta, remember, big O is at most about, big omega is at least about, and let's say theta just means about. Okay. With log n bit words, where n is the size of your problem. Okay? So this is the general model when you design algorithms. Now what this means is if your input is huge, you get bigger words. Okay? Why log n? Well, because if your algorithm runs in polynomial time, you're going to use at most polynomial space, and you can represent a number that's polynomial in n in some constant times log n bits. So this means you can store pointers. Okay. You can actually you can jump around in the space that you've been using. You can jump around in your input, and you can jump around in the space that you've been using for your computation. Okay, Karatsuba's algorithm, Strassen's algorithm. Okay, so that's the RAM model. So as long as you're working with numbers that fit in machine words, then you can assume addition is constant time, and in this class, let's assume that multiplication is also going to be constant time. And mod, let's say mod is constant time. Now actually, there are weird things like parity. You can't count the ones in a machine word in AC0. Whatever, it's in the lecture notes, but we're not going to care about that. So for not too large numbers, you can assume that arithmetic operations are constant time, and like usually you don't run into huge numbers unless you've got some psycho who makes you do something like count 4 colorings, which is like exponentially huge, and then you can get these really big numbers. But I think even for the 4 colorings of that map, it fits in a long, so it should fit in 64 bits. Okay, so yeah, we've talked about the RAM model, the input size. So let's just okay, now we have to talk about the complexity of addition. Well, let's look at these two numbers. 8, 6, 4, 1, 9, 6, 2, 1, 7533945. I told you that these will probably fit in a machine word on your machine, so you can, on your machine, your computer can add these in constant time, but how long does it take for a human being to do this? Okay. And this is important for Euclid's algorithm because remember I was talking about how many steps things took. But in order to talk about how much time it takes, we need to talk, if you're not assuming that your arithmetic operations, if mod doesn't take constant time, then you need to talk about how much time you need for arithmetic operations. Okay, so what's the standard algorithm for doing this? You go, okay, 6, 2, carry a 1, 9, carry the 1, 5, 7, 1, carry the 1, 15, 16. Okay? Now, how big can the carry be? Well, you can show by induction it's never more than 1 if you're just adding two numbers. Okay? Because when you start, the carry is 0, and assuming that the carry is at most 1, this is a 9, this is at most 9, this is at most 9, plus a 1 is only going to be 19, so the carry is going to be 1 again. Okay. So this looks, as long as I can add single digits in constant time, which I can do this in time proportional to the number of digits. So linear time in the size of the instance and the amount of paper that you give me. If you give me these two numbers, I can write this out in linear time, in the length of these two numbers. Okay, so addition is easy. Okay, now let's talk about multiplication very quickly. Not super quickly. But, so, how would I multiply? Well, how was I taught to multiply in primary school? 5 times 1 is 5, 5 times 2 is a 0, carry is 10, carry the 1. 5 times 6 is 30, so add 1 gives me 31, carry the 3, 5 times 9 is 45, I get an 8. 5 times 1, 9, blah, 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 blah. And then I drop down, okay, so this is all zeros. And then I have a 0 and a 0, and 4 times 1 is 4. And I do this for all of these numbers, and I did this in the lecture notes. So how many digits are in this big pile of stuff before I start adding up the columns? How long is this going to take me in terms of the number of digits in my input? Do I still have, are people still here? Yes. Well, some people. N squared, yes. If n is the number of digits, this is going to take n squared time. It's also going to take me n squared space, which is annoying, right? So I'm not just going to, it's not just going to be slow, I'm going to need a really big piece of paper. So you give me this on a little piece of paper, and then I need a big piece of paper for this. So there's a trick in the lecture notes, which I'm not really going to go through. But for example, okay, you can do this in linear space. For example, I can work out what this sum is. This is a 5, right? And then and then I'm done with this column. I don't need that anymore. Now I can work out what this column is, right? So I don't have this column anymore. So now what's this column? This is 5 times, so here the carry is a 1. And so I'm carrying this 1 over here. But the 5 is 5 times 2, this is a 0. 0 times 1, this is a 0. And then everything else is a 0. So this is a 0, I think. And then, okay, so now I had this 1 in the carry. So this is, I'm done with this. So I'm just writing this out. This takes linear space. Okay. I can do this. Okay, so 5 times 6 is 30 plus 1. So this is a 1, and I've got this 3 carried over. Now, 0 times 0 times 2 is a 0. And 4 times, wait, it's 5 times 6. 4 times 1 is a 4. So this is a 5. But that doesn't look right. 5 times 1, 5 times 2. Is that 505? Is in the course notes, is this actually 505? Yes, okay, this is going well. Yeah, okay, that's correct. Okay, so you can see that as long as I keep track of these pointers, how many pointers do I need? Well, at most 1 for each digit down here. And I can calculate these, I can fill in these columns and sum them up column by column instead of calculating them row by row and then summing them all. So I can reduce it to linear space. So now we've got multiplication O(n) squared time and O(n) space. Okay? So, now, that's, you know, okay, we're getting somewhere. We've got an improvement on what we were taught in primary school. But for a long time, you know, there are lots of different techniques for multiplying numbers. You know, you've got this, you've got these things where you count like different fingers and stuff like that. But actually, they're all going to be quadratic time. I mean, so we've been multiplying. Human beings have been multiplying things for thousands, probably just thousands, tens of thousands, maybe years. And we never, no. Big O, remember, it's not for best case, worst case, it's not for time, it's not for space. It just means at most about. So in another class, I'm going to show you there's this has anybody seen Stirling's formula for sort of, it's an approximation of factorials? Okay, it's got an O in there, right? And that doesn't mean good or bad. It doesn't mean time. It doesn't mean it's just a number. It means that this n factorial is like this, and then there's some difference which is like on the order of like n or log, something like that. I'd have to look up the Stirling formula again. Okay, so it hasn't got any semantics on it, apart from, like I said, at most about, at least about, and then we'll go into exactly what it means in another class. But now we have to get through Karatsuba and then Strassen. Okay, so there's this cool story that, so for thousands of years, we were multiplying things in quadratic time. And it seems like this is about the best we were going to ever do. To the extent that this famous mathematician, Andrei Kolmogorov, Andrei Alexei, I looked this up. It's correct in the course notes, in the lecture notes. Okay, so in a seminar in 1960, he conjectured that this is the best you can do. Okay, so notice that now I told you that computers can do this in constant time, but that's only for numbers that fit in machine words. So if the number is big enough, even the computer is going to need, if it does some standard algorithm, before 1960, even the computers needed, for very large numbers, they needed quadratic time to multiply, quadratic in the number of digits. Okay, so there was this student in the course 23 years old, Anatoly Karatsuba, in the seminar. And he went away, and a couple of days later he came back and he said, no, actually we can do it faster. And he showed Kolmogorov this divide and conquer algorithm that I'm about to show you now, which is kind of cool. Because the story goes that Kolmogorov was super impressed by this. Incidentally, if somebody does something like this to me, I promise I'll be super impressed too. To the extent that Kolmogorov wrote up the result with another algorithm about multiplication by somebody else and put these two people's names on it, not his own, and sent it to a journal. And so Karatsuba found out about this when he got the preprints, or the reprints, from the publisher, saying, congratulations, here's this very nice paper of yours that he didn't know had been submitted. And if you do something like that, I promise I will also write up your result and send it somewhere. I just if you could write on it, this was done in 3110, taught by Travis. But yeah, Dao would be super impressed. Don't worry, I didn't. It's like okay, yeah. Actually, I don't promise. I'm not as enthusiastic as Kolmogorov. It depends what you prove, but okay. So, what was Karatsuba's algorithm? So it's divide and conquer. So I have half an hour. Okay. So let's take this example. So I'm just going to have time to do the example, I think. Okay. So this is obviously. We can think of this as 8641 times 10 to the 4 plus 9621 and 7533 times 10 to the 4 plus 9405. Later in the course, I'm going to tell you about this Huffman's algorithm, which is this famous algorithm that he came up with to get out of the final exam in a course. I have to, my courses, they're not up to this level. Okay, so let's say, so we can split it up this way. So obviously, this multiplication is going to be 8, 6. Okay. Let's say that x1 equals 8641. x0 equals 9621. I have to remember how this goes. 7533. y0 equals 9405. Okay, so I don't have to keep writing this stuff out. Okay, so this product is x1 times 10 to the 4 plus x0 times y1 times 10 to the 4 plus y0. Now, the 10 to the 4 is just, the 10 is the base, and the 4 is n over 2, right? If the length of these numbers is n, then they're nice, they're powers of 2, n is a power of 2. This is easiest, but you can do it in all cases. So you could figure out, this works in general. Okay, so this is x1 times y1 times 10 to the 8 plus x1 y0 plus y1 x0 times 10 to the 4 plus x0 y0. Right? So this, you're just expanding this out, like first times this, this times this, this times this. Okay, everybody could do this. So how many multiplications is this? So instead of multiplying two n-digit numbers, I'm multiplying, well, I'm doing how many multiplications then over 2-digit numbers? 1, 2, 3, 4, right? Now that doesn't seem to have helped me, and I'm also doing a bunch of additions. Because 4 times n over 2 squared equals n squared, right? So this is the complexity of multiplying, roughly, the complexity of multiplying 2n over 2-digit numbers, and I'm still getting the same complexity just for doing these multiplications. Okay, so we haven't got anywhere. Gah, we're running out of time. So, what Karasuba, his trick was to come up with these intermediate numbers, where he said Z2 equals x1, y1. Z0 equals x0, y0. Z1 equals x1, y0 plus y1, x0. Okay? So that means that this is just Z1 times 10 to the 8 plus, Z2 plus Z1 times 10 to the 4 plus Z0. So far, nothing impressive. Okay? What was the trick? Well, he said, okay, but look, this still takes 1, 2, 3, 4 multiplications. But what happens if we notice that Z1 equals x1 plus